Hello and welcome back to Calculus, the series where we explore the applications of derivatives. First, I'd like to thank all the nice people that support the channel by liking and subscribing. Please recall, from the last video, we figured out how to find the maximum and minimum points of a curve. We did this by finding the derivative of the function, then equating it to 0, and of course solving for x. And then with the number line test, we would determine whether the points are a maximum or a minimum. However, in the end, we also came to the conclusion that if the derivative function has 3 or more roots, the number line test we use to determine the nature of the stationary point is not very efficient. Therefore, in this video, we introduce the second derivative test. After that, I'll show you what kind of points can be found with it also. Firstly, a second derivative is just the derivative of the derivative function. And we would denote it in the following way, f double prime of x. As an example, let's say we're given the function 3x cubed plus 4x plus 5. By the power rule, we know immediately that the first derivative would be 9x squared plus 4. So that means if we were to do the derivative again, we would take our derivative function and then do the derivative again. And here we would simply get 18x, which is the second derivative of the original f of x function. Okay, so now that we understand how the second derivative is computed, let's return to the example that we did in the previous video. We had the function f of x equals to 2x to the power of 4 minus 4x squared plus 1. And by the power rule, the first derivative was 8x cubed minus 8x. And once we equated that to 0, we said that we received 3 different answers. X can be 0 or x can be equal to plus minus 1. This means we have 3 different stationary points, each at one of these x coordinates. However, now instead of using the number line to determine whether it's a maximum or a minimum, we're going to continue computing the second derivative. Applying the power rule again, what we would get is 24x squared minus 8. Now that we have received the second derivative, our goal will be to plug these 3 zeros into the second derivative. So we compute f second derivative of 0, f second derivative of 1, and f second derivative of negative 1. The answers we get here are negative 8, 16, and 16. And now these answers tells us that at x equals to 0, we have a maximum, and at x equals to 1 or negative 1, we have 2 different minimums. Now you may ask, how did I come to this conclusion? When you plug the x values you got from the first derivative into the second, and you get a value less than 0, that means at x equals to 0, you have a maximum. However, if you plug in the x value and you receive the corresponding y value greater than 0, in our case 16, that means at x equals to 1, or in this case also negative 1, we have minimums. So let's put this into a definition. Here I will call this the second derivative test for maxima and minima. It simply states if the first derivative of the point C is equal to 0, and then when you plug that value into the second derivative and receive something less than 0 or negative, that means f of x, or the original function, has a maximum point at x equals to c. And of course, vice versa, if f derivative of c equals to 0, and you plug that value into the second derivative and receive something positive or greater than 0, that means that f of x will have a minimum at x equals to c. However, there is another case, and you might probably already be questioning. What if the first derivative of c is equal to 0, and you plug in that value into the second derivative, and you also get another 0? Well, this here is when I start talking about what kind of points can be found using the second derivative. Just like with the first derivative, if you equate the second derivative to 0 and then solve for x, these x values give you the points of inflection. Sounds like a mouthful, but it's really not that bad. Let's once again first visualize to see what's up. Let's say we have a function like this. You can immediately see that a part of it is looking downwards. In the middle, it is looking up. And again, at the end, it starts looking downwards again. This is what we call the concavity of a function. Concavity is mostly covered in quadratic functions, especially when drawing the parabolas. We determine the concavity of a parabola using the first coefficient a, seeing whether it's positive or negative. If it were positive, our parabola would be looking up, and of course, if the coefficient a was negative, our parabola would be looking down. However, for a complex function such as this one, concavity changes at a certain point. We could eyeball it, and it would be around here, where the concavity changes from down to up, and then on the other side, maybe somewhere here in the middle, concavity changes from up to down again. These purple points where we eyeballed, where we said the concavity of the function changes, are called the points of inflection. We find these points in the same fashion as the maximums and minimums. We first find the second derivative of the function. We then equate it to 0 and then solve for x's. And these x's would be the x-coordinates of our points of inflection. And naturally, if you want to find its corresponding y-coordinate, all you do is plug it into the original f of x function. Let's say solving the second derivative equals to 0, we get two answers, x1 and x2. Again, just like the maximum minimums, we can put these points on a number line. Once again, putting it on a number line, we get three different intervals. And just like before, we pick three random numbers from each of these intervals. So let's say I denote these numbers as A, B, and C. And then I take these three randomly chosen numbers and plug them into the second derivative. Let's say the answers I got are the following. F second derivative of A is greater than 0, F second derivative of C is also greater than 0, however, F second derivative of B is less than 0. In other words, positive, negative, and positive. If the value is positive, that means the interval at which the function exists is concave up. This tells us from negative infinity till x1, our function would be concave up. And from x2 to positive infinity, it would also be concave up. And in contrast, since f second derivative of b is less than 0, this means in the middle from x1 to x2, our function would be concave down. However, there is one special case that I would like to speak about. Most of the time, when we put in the zeros on the number line and then determine the signs of the interval, we have alternating signs, such as in our example, we had plus, minus, plus. However, there can come a situation where you have two of the same signs repeating in a row. For example, in the first two intervals, we have plus and plus, and then in the last one, we have a minus. So what's happening here? This is basically telling us that our function is concave up, and then it also became concave up again. Well, this in reality can actually happen quite often than you may think. So let's first visualize this on the graph. In a graph like this, you can see originally that the function is concave up, and then it grows and grows and grows and reaches a certain point somewhere in the middle, where it wants to change concavity, however, it was forced up again. So you can see here on top, it's technically concave up again. And only then it reaches another point of inflection and then becomes concave down. So the first point at which concavity was forced to not be changed, in our case the x1 point where we have two concave ups in a row, this point is called the horizontal point of inflection. This can actually also happen when you have two minuses in a row. That just means you have two parts of the function that are both concave down next to each other. All this information seems extremely overwhelming, so let's take a look at an example. We are given a function y equals to x plus 1 times x minus 3 cubed, and we're tasked to find the turning points and the points of inflection. So immediately, we need to first compute the two derivatives, first and second. I can immediately tell you these two would be the first and second derivative. Here, we simply use the product rule for differentiation. Oh, and an alternative notation for the second derivative could also be this. So now, solving the first derivative equal to 0, we get x equal to 0, or x can be equal to 3. And then we apply the second derivative test in order to classify whether these points are maximums or minimums. At 0, the second derivative is equal to 36, which is a positive value telling us that at x equal to 0, we have a minimum point. However, here comes the interesting part. When we plug in 3 into the second derivative, what we get is 0. We don't know if that is positive or negative. 0 does not carry any sign with it. So immediately, this information will tell us that at x equals to 3, we don't have a turning point, rather we have a horizontal point of inflection. Well, this has been a lot to digest. This has been one of the longest videos I've ever made. So take it all in for today. And in the next video, we will take a look at the derivatives of trigonometric functions and logarithmic functions. Also, I will speak a little about the Euler's number. So I hope to see you there and have a nice day. Bye.